So what else can we do when two waves meet? So here is a sort of more general thing. Instead of having two identical waves, I've now let the frequencies be slightly different. So as you see in the label there, this is 5 and 6 hertz oscillations down here. So remember, that's the frequency. That is the number of cycles per second. Period would be 1 divided by that. I've got my time axis there and my amplitude over there. And so the red and the blue are the different frequencies, and this purpley curve now is what you get when you add them together. And so what you see is with these slightly different frequencies, you kind of get some constructive interference. In fact, right here, you're getting sort of perfect constructive interference. Over here, you're kind of getting more cancellation, so you're getting some destructive. So there's always a case of partial constructive or partial destructive interference that's possible, but there's actually something more going on here. The overall wave is doing some sort of nice sinusoidal variation in its amplitude, but oscillating within that overall envelope. Okay, so we call this outer thing, this dashed line, the envelope of the oscillation, and inside it we know that we've got some even finer oscillations. All right, why is this useful? Well, to see why this is useful, let's take a look at some of the maths and then see some better examples of this as well. So this phenomenon is something useful called beats. So let's take a look, as I say, at the maths. So it's only possible with two close frequencies. And in that case, what you can do is you just look at this formula. We're doing superposition, so we're supposed to add things together. So we've got one wave with frequency 1 and another wave with frequency 2. They've got the same amplitude x. What do I get when I add these? So depending on how much you like your trig formulas, you can actually show that this is transformed into this expression. It just becomes twice the amplitude times two different cosine functions, one which varies as the difference on 2, and one which varies as the sum of the frequencies on 2. This thing here is known as the prostaphoresis formula. If you want to, you can look that up. Okay, it's just a bunch of trig identities of how you can manipulate sums of cosines and things like that. Okay, why is this useful? So we rewrite it slightly differently. We'll go, it's 2x times the cosine of just pi times the beat frequency times t, and cosine of 2 pi times the average frequency times t. Certainly we recognize that as an average. And this thing, we just extract the top part as the beat frequency. And we've put absolute value because we know that cosine of x is the same thing as cosine of minus x. Okay, so using that information, we can say that certainly I can put absolute value on this, and this then is exactly that same expression because the 2's go away, and I've just added the absolute values basically for free to that statement so that we can always talk about positive beat frequencies. Okay, so the beat frequency is just the difference. So here I would have 5 and 6 with a difference in frequency of 1. That doesn't really help me too much. But as I increase the actual frequencies, so here I've got slightly higher frequencies, you can still see the oscillations. You can see the envelope now, okay, with its sort of 1 hertz frequency. Why is this useful? Well, let's step it up one bit further to frequencies that we can actually hear. So if we think about this, we've now got 438 and 442 hertz. So looking at this thing, we can no longer really see the individual variations. They're very small as they're really high frequencies now in this time scale. But even though we can't really see the variations of that one, we can certainly still see the variation in our beat envelope, which is going with now a difference of 4 hertz. So therefore that is our beat frequency. So we can't see the individual variations of the waves themselves, but the superposition is a very identifiable sinusoidal variation. And this is actually a key thing to how we tune instruments, for instance. So here is the sound of a 438 hertz. Here is the sound of 442 hertz. And lastly, let's listen to their superposition. And you can definitely hear the difference. This thing now is clearly doing a loud, then soft, then loud, then soft. And so you know that these two, which sounded quite the same, are actually different. And what you do is then you tune one of them until you make this beat vanish, because it basically ends up, if they're the same frequency, then you get no beating